It was a microphone.
Okay. It's distracting me. Maybe a little bit, okay. For visual privacy, according to legal reform, of rewards can also contribute to employee stress and dissatisfaction with working experience. Nevertheless, the protections of to open plan office differ from person to person. Those clinic crowd can be located in private offices as moderating spaces. Furthermore, people with different work types also have relative requirements to privacy. So how can we ensure those private spaces and shared spaces such as kitchen are located in appropriate in the workplace? We need a special data optimization workflow to inform the design decision. So here we come to the research question. How can visual and acoustic privacy measures be integrated into the creation of an early stage design? In this project, we will aim to build our workflow which will be able to evaluate both visual and acoustic privacy at early design stage and multiple ideal decision-making data for optimizing the existing software to achieve a private workplace. At the workflow setup stage, the first part is to set our concept of plan. This will observing the relation between partitions and the facility type allocation. All potential positions of partitions are identified. The interior walls are assigned according to the facility type. Only concrete and glass are being used in this research. The exterior wall has set as glazing facade only to make the design more realistic. This diagram illustrates the detailed setup workflow. Lists out the information that users need to provide before privacy evaluation, including the constants, variables, objectives, and materials associated to each type of facility. After setup stage, here we come the visual privacy evaluation process. This step is implemented using the plugin of decoding space. Generally, it is for urban design usage, creating street networks in buildings, etc. But the evaluation tool can also apply to single purpose. In short, we search for ideal decision making data out of floating data and apply it into the entire workplace to evaluate the visual performance. After average of each store are calculated, we remap the data for regulation and compare it with objectives to check consistency. This is the decision-making data selection process. A working experiment has accomplished voting the best data for area according to opportunity and complexity. Usually, the aim is to observe the visibility of each zone from points inside the workplace. The exterior wall has restrict your vision in order to narrow down your attention. Feel free to imagine that you can see through the data. Anyway, area has one, so it's clear and intuitive implication to this space. It's such an area that you can see from the point. After we decide this area as decision-making data, we apply all the points on the workplace as subject points to visualize this area heat map. The color on the heat map indicates the extent of that space can be seen by other provisions. The average data of points from each door are calculated and is mapped onto second diagram to visualize the privacy extent of each space. The third one is a decision-making diagram which will map the average compared with the objective domain. The included data are codified as true and the others are false. For acoustic privacy, Python is a plugin used for implementation. It calculates material properties and sound information in order to generate complex and valuable data for complex analysis. Due to the technical limitation, the core functions are not in use. When you normalize, the resolution time was isolated from this plugin as Python took decades to calculate. Hence, only visualized ray tracing component for Python was working in this research tool. This slide specifies reverberation time use calculation technique using the Traversal formula. Reverberation time indicates the time for level of the sound to decrease about 60 decibels. Hence, it is a special attribute which is used to represent the whole effect of interior space. The V is the volume of the space. S stands for the surface area. A is the average data of absorption coefficient. In terms of reverberation time, the noise reduction coefficient, which is R, used to symbolize the sound absorption. The hierarchy corresponds to the brain-free material used in this research as walls, standing, and floor. And the blue table is the authorized reference for objective domains referring to some types of facilities. This video represents a similar implication with the visual privacy decision-making process. But reverberation time is a factor that only facility type allocation could determine. Partition attributes were completely disregarded. Ray tracing technique is a core section in acoustic privacy analysis. For high efficiency, I divided the space into 3 small sections. The first part was to assign image source onto this space. Image source output wave actions for source points use a filter delays for by their lenses in order to ensure the most effective data usage. And there were 2 types of ray tracing implementations, merging components as one model or classifying in different materials. The first one is correct usage of model control, but it ended up with stubborn ray propagations without any transmission to material. The second one isolated each type of components as individuals. It doesn't comply to the design intention of Parkinson designer authors, but I found it feasible in this research. The retracing decision-making process is also similar to previous one. The amount of rays determine the acoustic privacy index of the LVH zone and the relative polling data to their users if the zone complying with the objectives. This is a detailed workflow diagram. The workflow can also apply to other types of topologies, such as floors or vectors, as long as the given floor plan has clear boundaries to facility space and open space. Worth notifying is the output of the workflow. One optimal design solution generated for optimization is considered. It is completed, but regarding to some future implementations, I created a video out of a series of design options. This video represents the model information of some random design options, but the last option represents for the optimal design. The radar graph on the left-hand side, on your left-hand side, indicates the number of zones complying with relative objectives. The middle ones detail the model information of each zone. What is model of each zone, and the blue hatches are the objective domains and the white ones are calculated rates. The diagram on the right-hand side illustrates each zone here where users can be informed about the quality of the design option. Accordingly, the design team can also be informed about the revealed in the optimization. Overall, this research produces a workflow which simultaneously evaluates mission and the acoustic component, and consequently generate optimal design which best meets both sides of performance criteria. It also creates a visualization method that highlights this optimal area for visual and acoustic. This aims to assist designers to review and implement their design solution. The Parkinson core function is the course, its main research limitation, and some transmission index of also appropriate decision-making data for costly evaluation. It represents the speech intelligibility and having material properties as part of the calculation when defining the acoustic privacy index accurately. But the plugin processing time was excessive. The complexity of the workflow can be reduced by developing a user interface for workflow setup data, platform where users can type in the predefined input. A rate of design involvement referring to the depth of optimization can be alternative to design application. Not only partition attributes can be used as variables, the dimensions of zones can also be flexible. The rate of privacy type priority indicates the relative importance of privacy type switch opportunities to invite potentially feasible design options for optimization. The second future research approach is to develop a user interface for reviewing the design options. This video refers to the Explorer designed by Core Studio. Users can select the subdomains from attributes in order to search for it. In other words, the user interface like this incorporates user preference into the workflow, which can bring far-reaching and profound meaning to future research applications. Special design outcomes can be enhanced by augmenting the skills of designers through computational decision support workflows. Hence, what else can computational tools do to assist designers to narrow down their actual concerns and help them concentrate on design parts can be the future research implication for computational design. Look at them. I'm just worried about time. All about the time. Yeah. Okay.
I see that we have trying to you think that with your students back there, that it could be possible create a specified segregation, the explanation for that. But right now, congregation, no, you just or when people who look at this say, I want to hear a meeting, right? Like, so we know people who think that there's you with this location, that area, for that. Yeah, I mean, right now you have the size of the room and everything, and the location of the room is already set. No change.
Now, well done with a really good research project. I think a really nice frame that I think we are going to be quite interested in seeing that. Because what all this research is doing is really focusing on sound, but he acknowledged actually now sound and visual and other things become all into a mixture. And we show projects where maybe they've done the kind of structural engineering, acoustic engineering, solar engineering, climate engineering, all come together. It's very interesting to throw out. Are there any questions from the audience? Madame, you take off the board. Yeah, exactly, yeah. So you are called by names on the author side. And did he respond? There's completely kind of advice for all of you if you have problems and you know that somebody has done that kind of stuff. But the meanwhile, if you're called, why not take it? For being a mother of a child, you like to talk about your family. Oh, ask me about that. All that questions. All right, Billy,
rock and roll. Morning, everyone. So,
can you sit down by the way?
can we?
Yeah, yeah.
Oh my God.
Still getting embarrassed here. Sit down.
This is the most casual research presentation ever. Nice, thank you.
The whole term you didn't really stand up by.
No, I've been sitting at my desk.
All right.
Okay. That's good. Morning, everyone. So today I'm going to talk about my research project that I've been doing over the past 10 weeks. So in collaboration with current architects, my analyzing view quality using a 3D isoburst ray tracing to inform decision-making in a multi-story residential development. Developing a project in the built environment is a difficult task in itself. When trying to quantify and metricize different aspects of the building that are subjective in terms of a user's perspective, the difficulty is then multiplied exponentially. View quality from within an apartment is more specifically significant to occupants and an apartment's market value, but is often described in subjective terms and is less easy to communicate in quantitative values. For these reasons, view quality is less likely to be addressed as a parameter in the early stage of design that can be explored in relation to other more readily parameterized environmental phenomena, such as solar or wind access. So to give a bit of an example, this is an apartment on the 31st floor of a Foster & Partners architecturally designed building. For 31 floors on the west side, it is blocked by another building. My research aims to change this problem by asking the question, in what ways can external view quality be measured in a multi-story residential development to better inform decision-making? The main aim of this research is to develop a tool that can analyze and quantify the quality of a view from a room. Originally, the aim of this research was to analyze the room, but it was also to incorporate it in a multi-objective optimization workflow that would also incorporate Monica's wind optimization as well as other environmental phenomena such as solar and other phenomena. So originally the aim was to incorporate the analysis tool, but it was also to adapt the STEP 65 apartment design guide to optimize the layout of the floor plan and provide a better quality view while also balancing privacy. So the tool produced was able to analyze an MSRD, however, it was only able to achieve this within a limited scope, only being able to analyze the views using test geometry of the surrounding context rather than the actual geometry of the city of Sydney. So I'll explore those limitations later in the presentation. So collaborating with Crone Architects, this research uses a case study of an MSRD in adopting a research methodology. It's defined by O'Brien as problem solving using real issues and problems in a limited time frame. Incorporating the methods used in the study of human ecology, action research also looks to modify and affect the environment it is based in. Following a cycle of planning, acting, observing, and reflecting, the tool was developed in stages over the 10-week period. The site of the case study is located at 175 Liverpool Street, Sydney, and it's situated at the southern end of Hyde Park. Currently, there's a commercial tower there occupying the space. The site is bordered on the east and west side by residential developments and on the southern side by medium to high-rise commercial buildings. Previous research in the area of analyzing and optimizing view quality is scarce. Most research focuses on view in the scope of privacy and urban development. The earliest use of computation to analyze the view's quality were Lee and Will in 1997, developing a tool that analyzed the view of an MSRD in Hong Kong. To test the quality of view, Lee and Will developed a set of fuzzy criteria. So in discussion with Crone, it was decided to adapt these criteria to the analysis of the site in Sydney. Lee and Will's used image processing of low resolution images to produce their analysis. But it was suggested to use the 3D isoburst tool. So following Lonegren's and Headley's research, they developed and adapted 3D isoburst tools to analyze a number of different criteria with isoburst tools. So the different criteria they analyzed was privacy of apartments in MSRD in Toronto. They focused mostly on the classification of different isobursts, and the relation it has with the geometry of observing, differentiating whether an isovis is produced from a point, a path, or a volume. The future focus of their work looked at integration of isovis with GIST to better analyze with the analysis of multiple viewpoints in the research, it forms an isovis volume that, so my analysis forms a volume isovis. So the main tools used throughout this were Grasshopper and Rhinoceros and the analysis was performed using the Decoding Spaces toolbox, and the TT toolbox was used to and calculate the data produced from the 3D isovis. So following a process to design created early in the research project, this was the roadmap for developing an analysis tool. The model of Sydney that was to be analysed was purchased from CADmapper when open source solutions were proven too difficult to produce. Because of the large amount of time and massive amount of data produced when analysing the Sydney model, it was decided to produce the analysis tool using a low poly mock-up of the cityscape. The different elements of the model were then divided into their classifications. The criteria being analysed were decided upon to be ground, paths, water, buildings, points of interest, roads, extent of view, and the amount of sky in the view. This is the full view of the analysis of this script. As you can see, it's quite extensive and some parts don't work quite as well. So here's an output of the analysis from a top-down view, just showing the view range or that the isovis rays create. So the first part of the script was generating a context. So this is just using a grid and a random number of random variables to just generate sizes and heights, just to sort of generate a simulacrum of a city. So the next part of the workflow was to generate a tower. Crone did provide a 3D model of a tower that they were developing, but it was decided to develop another script that could generate a tower itself that could be adapted for a multi-objective optimization workflow. So the tower generates points, and from each point, these get fed into the viewpoint, into the ray tracing solution, so 3D isovis, and this generates the analysis. So 3 minutes, 4 minutes, okay, all good. So the ray tracing produces an outflow. It takes a number of inputs, viewpoints, obstacle surfaces, ground surfaces, and the view direction. So which vector is the room facing outwards. Then you can set the length of the view, how far, how many rays are used, and so on. And it's using a GPU to analyze the process. It can also use CPU, but the results are quite varied between the two. So because of the massive amount of data, it was I had to try and find a solution to store it, because when I stored it in the Grasshopper file, it became massive and it would crash very often. So writing it to an Excel file, then reading it, provided a good solution using test geometry. When using the real 3D geometry of the city of Sydney, latency was incredible. It would take 5 minutes just to unblock plug a component in or unplug a component for it to just run again. So visualization is quite simple. It's just using gradient and some simple sums and maths of like the percentages of the amount of like what's blocking what. This is an early example of the analysis when we were just testing the front facade. Here's just this little animation showing the rays going around the entire perimeter of the thing. And so without the rays, it shows what buildings are interactive. So the red so from red to green, red means the more rays are hitting that building, green means less rays. Showing the interaction of the user interface with an earlier prototype. So future research. Future research is looking to bring in the full model of the city of Sydney, determine different methods of view quality using machine learning or image recognition and social media sort of scraping to try and find maybe what's the best view or what view has a high number of interactions, or ecologist studies. And it also, other research is looking at updating the 3D IsoVista or replacing it with another custom-made script that can sort of perform better and produce results that are able to be computed without a large amount of latency. So in the end, I ended up creating a view analysis tool. The only problem is it doesn't quite work with actual geometry. It only works in any test setup. So the next thing would be to look at developing a tool that can better. So limitations were the analysis, file size, script latency, computing power. Trying to do this all on a laptop was very frustrating. As you can see here, these sizes of the files increased exponentially. So using the full context, the file turns out to be around 90 megabytes, and importing that into Grasshopper, it just tanks it so much. Sorry, not very scientific. But thanks very much for listening to my presentation. Sorry. Thank you. It's good to see you in a while.
There are some research
Yeah.
So how you calculate that in the
Yeah, yes. So the third output down, that's length. So that's the length of each ray from the point of view to the obstacle it hits. Yeah. Yeah. Yeah, points of view. So you can see the purple, if I go back to the main, sorry. Either way. So the purple towers, they've been designated as points of interest. So using the so if a ray hits that, come back, it'll tell me it's hit this piece of geometry or this building here. So I might multiply the score that it gets for that to increase saying, so this is an important piece of geometry. If it was the real Sydney, it might be Westfield Tower or Sydney Opera House, just depending on where it's located. But yeah. Yeah. Bill, I did download the data from CAD Mapper. It's about 20 megabytes. Its problem is the ray tracing analyzes meshes. So depending, because the data is open source, it varies widely with the amount of faces on the meshes. So using the full geometry from CAD Mapper, it returns about 20 million results, and that's quite intense. So the next step of the process would be to actually try and figure out a way to sort of reduce the latency of the data. So either putting it into a Python database that can easily be accessed faster than Excel, faster than reading and writing from Excel. Unfortunately, I had to use test geometry because that's the only way I could actually test the view and show that it actually interacts with different elements, so water or greenery or points of interest. Yeah. Yeah. Yeah, I'm taking into account full of windows. So the next step in the process of future research would also be taking the actual building that Crone got or Crone provided and using analysis of the facade as well. So setting a viewpoint in the room, but it also looks out of the room and actually interacts with the facade or obstacles blocking it of the actual building itself. All good.
No, well done. I think really a great way to use potential in the tool. And yet the tool was not completed to the ambition that it given.
No, yeah.
But that will never happen. You know, you set yourself a goal and you work towards the goal, and all research projects I ever supervised with the second aspect. You understand what you need and you work towards it, and you find out after 10 weeks or 12 weeks or 60 weeks or 100 weeks, it always takes longer for them. Very, very well the roots of the project. You have identified strength in terms of whether it be great in a real city model, but unfortunately the models that are available are not as good. But if I would be working in an office, I would tell them exactly what their city model needs to have in order to work.
Yeah.
Work. Here having the starting point is only half of the moment, but they have further potential to say, okay, I'm going to put the window in there, or if the building fresh with a new building, maybe let's move the window from here to here, because then you can see the opera house with the MRT is optimized.
Yeah.
Design.
Yeah.
Well done. I think it's really has great potential, and I hope you find a chance of a firm that just gives you the chance to develop that tool further. I think there will be a few firms quite interested in that, because you can increase the dollar value of each apartment by not just a dollar, but by 100,000. So the apartment I'm living on the 18th floor is $200,000 less worth than on the 19th floor or the 20th floor.
Yeah.
Or 21st floor. Just recently had been a sale on the 17th floor, one floor below on the 21st floor. Same apartment, different view. So you can see more of the water, you can see more of the things. So with you, Julia, you need $100,000, and that's just going to generate that abuse, and you make a fortune as a developer.
Yeah. Yeah.
Good,
Thank you very much.
I have a quick question.
Yeah, that's all good.
When you were prototyping, obviously,
Yeah.
always the once did you attempt with a geometry? But
No.
like, just like in one level of a curved geometry, how does the calculations like vectors and for like how the
So the vectors, it's a for vectors, it's a bit interesting. Oh, are we looking at that? Sorry.
not all like if there's a curved window, not all of its vectors will have a corresponding
Yes, actually, that was a problem I had here. Like, not all vectors, as you say, are corresponding. With the corner room, I had to take them out separately and analyze them separately because the angle, because just setting them at the normal horizontal and vertical viewing angle for the forward-facing apartments, it was limiting the view.
Yeah.
So a corner view might be like that, but at the moment it was that, and it was missing out on huge amounts of geometry you could actually see and interact with. I'm trying to adapt it for irregular geometry. That seems like, yeah. The problem is trying to match up the data with the, like trying to match up the vector data with the point data coming out. So like, yeah. Yeah, that's all good. Yes, immensely. I'm still struggling at the moment with these corner points, trying to reintegrate them when they come out of them. So when they come out of the visible mesh down the bottom there, when they come out, it's structured in two separate branches, and trying to combine them and get them to follow the same like point system, like the same direction, is quite difficult, and I'm ending up with like 0, 2, 3, 1, 4. Yeah. Yeah, handling data was the biggest task of this research project itself. Yeah.
Sorry, guys. 600 bucks an hour. Sorry, guys. This is. I know it gets randomly. No, like all my passwords are randomly generated by a server, and it gets changed every like 3 days. So I never actually know the password. It's all linked to my fingerprint. And now two-factor. Also proximity to the sign-in, IP tracking. I got a corporate account. So yeah, IP tracking, like it actually knows where I am, and it won't let me log in if I'm too far away from the login point. Shit. Okay, well the disk is full. How do I? So I can't download it. I can't download it. Okay, how do I present from? Is that okay? Wait. How do I get it into presentation mode? Do you want to help me? Bullshit. Oh wait, hold on. Presentation.
There you go.
Oh, thank you.
I
think. Okay, that's not gonna. No, sorry, that's not good. Can somebody else go and I'll come back very quickly? I'm wasting time for you guys. Sorry.
on Teams and everything. Right. So, multi-objective optimization of facade glazing. So, applying computational tools in early stages of design through environmental simulation and optimization. So, the problem. Global warming is one of the biggest issues humans currently face. The Earth is getting hotter. Due to that, ACs currently account for 10% of all global emissions, and that's expected to triple by 2050. Due to that, HVAC use accounts for 61% of one single building's energy use. Therefore, designers really need to start considering more sustainable design decisions within their processes. Decisions such as how can glazing choice impact internal space performance. So it leads to the research questions on this paper. How can glazing choice decisions impact the thermal performance of internal space, and how can computational tools assist in this decision process through environmental simulation and multi-object optimization. The objectives of this then is to construct a grasp of the script that can quickly test and analyze the impact of glazing choice on the conditions of an internal space, create a robust recipe within that script that can generate adaptive window-to-wall ratio and shader systems, and then implement a multi-objective optimization system within the same script to refine the results generated. So it's broken down like this, an energy simulation that feeds results into a multi-objective optimization system. So it runs through using the grasp plugins Honeybee, Ladybug, and the database Plus, and then uses Galacticus and Wallasey to optimize those results. Break down the workflow. It starts off with a 3D model that is transferred into a Grasper environment, and that Grasper environment features a parametric script that will feed results into an optimization system. And this process is cyclical and feeds back between those 4 elements. Starts off as a 3D model. So this is a 3ds file, Sunshine Coast University Hospital, provided by my partnering company, BIM Consulting. The entire model has been broken down into 5 rooms. And for this project, I've decided to use 1 room. It uses a basic box structure, the approximate size of the room, to allow Honeybee to run efficiently, and also allow Honeybee's Energy Plus database material allocation. The windows are also generated within on this system. To break down the script, it starts off there is meant to be text there, but it starts off at the window generation at the start, which is the parametric element where user input is able to be input, and then the geometry setup, which will create the setup for the energy simulation after that, and then the results at the end. So the zone allocation is the beginning part of this. So this is the assigned to each geometry layer of the exploded box with a layer type, so a wall, ceiling, a floor, and this can allow for appropriate material allocation within the Energy Plus database, and that assigns material attributes to each facing. So that could be for a wall, it would have a gypsum, an insulation and timber layer for that wall. This is also the system in which the glazing parameters are applied, so that attributes what the single EP material component. This includes the frame as well, so just worked out better. It also features a U-value, solar coefficient, and visual transmittance attributes as well. To run the simulation, it uses the Energy Plus component, and then for context, provided the EPW location of Brisbane, and then the analysis period at North Point, and then the comfort matrix and sunlight hours to produce the results. The parametric element of this is the adaptive window and shading generation system. So the windows are generated onto a window wall, and parameters are created to control the window to wall ratio. And then the adaptive shader system is also created on this to generate louvers, side and top, and slat shading for these. And these are all adapted to the window sizings. So the results, so what I'm testing for is adaptive thermal comfort, which is the number of occupants within a space that would find that internal space comfortable. Anything around 85% is considered acceptable. So further on, internal operative temperature is the average mean radiant and ambient air temperature. And then the primary testing period I have chosen is summer, based on the location being Queensland. The harsher conditions within the site are during summer. It's also just due to simulation load. It takes about 2 to 5 minutes to run a 3-month simulation, and it takes a lot longer when I'm running annually in winter as well. Due to that, we use summer. So looking at the results, so I have a 3 window setup with the original roof, and that's a 2 by 2 meter setup. So when looking at these results, the results aren't as substantial. You're seeing single glazing and 86.6% comfort rating, and then double glazing and 90.1% rating, and then a ½ degree drop within that space. When increasing the size, the results become more substantial. So at a 3.1 by 4.2 window setup, you're looking at single glazing with 60%, and then double glazing at 83.9%, and then a 4 degree drop in temperature. When increasing the size to be a complete curtain wall, in this case a 15 by 4 meter glass facade, the results are a lot more substantial, with single glazing at 48.6% and then double glazing 78.1%, so still remaining close to that acceptable range, and then a full 2 degree drop in temperature. So how about the rest of the year? I did test for winter. So in winter overall, I saw about 8% increase in performance. So the double glazing was able to retain the heat a lot more effectively than single glazing within that period. And then all year, I saw a 20% increase in thermal. So in testing the shaders, the top shaders and the side shaders provided a 2% increase in thermal performance annually, and then the louver shaders an 8% increase in thermal performance annually. So in testing lighting, I did test lighting. In terms of visual transmittance, the impact of that slider didn't make a large impact. It was more so the window sizing that had a bigger impact. In summer, there are more substantial results with more light entering the space during that period. So change of orientation, the original building is originally facing north to south. Through changing the orientation just to test the results of changing east to west, there were more substantial results with a better comfort, a more substantial comfort rating and a large more amount of light entering the space as well. So moving on to the optimization, you have Galapagos, which I started with. Now that's a single objective evolutionary engine, and it was really slow, it would crash a lot, and it just wasn't suited for what I needed. So I moved on to Wallasey, which is a multi-objective optimization plugin, and this is a lot better in terms of providing performance indicators and an overall more robust system that was able to be run faster as well. So the goal of this was to maximize operative comfort and minimize operative temperature while maximizing daylight levels. So just break down this optimization process within Wallasey. It begins as genes, so these are parameters, in this case, the windows and the wall sizing. The objectives, so these are the results from the simulation that are fed into that objective component. And that is, in this case, was the goal to maximize comfort whilst maximizing daylight levels as well. And then the phenotype, which is the geometry being inserted, that will then be used for exporting that geometry, the changes of the iterations being made into a visualization, which will feed results. So the way this works roughly is Wallasey will create generations, and then within each generation, there's a number of iterations that can be depending on what you choose. I think I chose about 10 iterations per generation. So around 100 different iterations per result. Yeah. And then moving on to single glazing, and then the results from that optimization process. So the 3 original windows at a single glazing setup. The optimum sizing for that I found was about 3.5 by 2.8. And then for setup in double glazing, it was 3.1 by 3.8. So a marginal increase. In terms of just testing one singular wall, I saw that there was one singular window. I was able to just test the window to wall ratio specifically. And this was just testing the limits of what I could push single glazing. So with single glazing, it was about 20%, and then double glazing was 60%. So a 40% increase through using double glazing in that regard. So we're making evaluations on this. The 40% increase in basic window to wall ratio through using double glazing. The maximum size for a 3-window single glazing setup was 3 by 3. After that limit, it's just more appropriate to use a double glazing. And then value site into exploring the limits. And that's where I think it becomes important. As you can see with the graph, the setups of 3 windows at 2 by 2, the 3 windows at 3 by 3, the results are quite close in that regard. So in terms of using windows that are smaller sizes, you can still use glazing. And then as the windows get bigger, the standard deviation does increase, and it becomes more appropriate to use double glazing in that regard. The objectives were met. There are still some limitations. So processing time is very slow. It still requires basic grasp of knowledge in terms of a tool being implemented into a designer's workflow, and then it hasn't been tested on curves. So I think in ways of taking this further, I think creating a way, making this form of testing accessible to a novice grasshopper user, and make this form of simulation more feasible in early stages of design through providing a tool or an interface that would allow a designer with no grasp of knowledge to use these within their early stages of testing. And then also increasing testing variety, increasing the processing speed. In regards to speed, the new updated Ladybug tools did come out, which supposedly increases speed, but there are no microclimate analysis comfort mapping tools yet for that. In wrapping this up, I'd say that it led to an understanding and refinement, a greater understanding and refinement. So through visualizing the impact of material performance and window sizing, and then the increased processing time to test a mass range of variations, it ultimately led to a greater understanding in a shorter amount of time.
One question. So I see that you basically are able to modify the size of the window. Would it be possible to define data definition that allows you to modify or to locate one particular window that the system is about the best over.
Yeah. I think that would be a good step in terms of improving that. I think window allocation is the only area where it needs a bit of work on. At the moment, it just plants itself in the middle of the wall, in the middle of the wall, and then I can choose how many windows I want within that system, and then go from there. But I think that would be a good way of. Yeah. Okay. Not that robust. I think at the moment, like I said, curves. So I think planar buildings, if it's a box structure, in terms of this, the user still has to create a box within Rhino. So to create that room. So, and that would be their space. So in terms of, I think, I still have to, like I said, increase, I think I said here, increase testing variety. So it would be in regards to that. So improving that workflow through that workspace. But yeah, in terms of this building, it works on this room, but it still needs to be tested because I was using the things. Yeah.
Greenhouse. Yeah. But then
Really?
And having a tool that shows you that available to all architects that really can see that our benefit performance very, very good. So well done.
Thank you.
Thank you. In general, seeing our last project, that brought I'm not sure if the last only open that or not. I assume these are bachelor students in the second, third year, and they learn about the wall that is on the former practice problem, mediocre from a continuous problem, mediocre from a patient that should teach that rubbish students, so they should bring that rubbish to the outside world and see that it's actually and see the level of using offers. Sophisticated tools that using and now how that normally only exists at the higher expert level. The criteria tools might not work 100%, but if in weeks that still use more. So I think you quite often don't understand the value of knowledge and over and over.
don't know what to do. Hi, please. Oh my God, thank you.
All right, do we do the meantime, Jane?
I do have this. I never assumed that Apple will have no level.
Okay. Hi, I'm here presenting my work on a hospital floor plan optimization using multi-agent based simulations with HDR. Let's start with addressing the problem. A floor plan has three main components: its walls, its entrances, and its points of interest, which can range from desks, chairs, and other objects that populate the floor. Excluding entrances, these are essentially obstacles between you and your destination. These obstacles, arranged awkwardly or with intuition without further regard, can impede your trip, wasting your time as you zigzag through oddly placed furniture, walls that don't let the space breathe, and bumping into other people. Let's zoom into the I think it's on a timer. Let's zoom into the context we're focusing on, the hospital. Time is a luxury there, and a few seconds saved in the operating room could save somebody's eyesight, seal an artery, or even more. My research aims to provide an approach that borrows time from the trip to the operating room into said operating room. This brings me to my main research question. How can multi-agent simulations increase traversal efficiency in a hospital environment? My objectives and outcomes involve focus on optimized traversal efficiency. A hospital setting was chosen as an increase in traversal effectiveness could be an improvement to one's health. Going more into detail, this means I aim to reduce the time to reach the destination for profile groups, such as patients and the general public. Reducing congestion is also a major objective, as it is vital in the agents reaching that destination in a quicker manner. My workflow consists of an initial input of a floor plan, which provides point of interest locations. The plugin PedSim is then implemented into the floor plan. Heat mapping and route timing is then recorded onto the existing plan. Other information that PedSim provides, such as pathing, is then utilized to create an optimized floor plan. Before we're finished, the floor plan has to be tested and compared to initial results before we can truly call it optimized. Step 1 is placing the hospital floor plan HDR provided me into Rhino Grasshopper. Looking closer, we can see the specific area I want to implement my research, which is a public area. This area has been chosen due to its selection of user profiles, which are more scarce in staff, giving me an easier understanding in their routes and activities within the time constraint. This area has been altered into closed polylines to cater to the plugin that enables agent simulations. Thanks to floor plan, points of interest such as seating areas and kiosks were able to be located and implemented into PedSim. Time to visit was vital in differentiating different interest points, as agents would stay longer at seating areas than kiosks. Different varieties of routes were scripted to authentically map agent path directions. A variety of locations are included, such as the main entrance, pastoral care, the elevators, stairs, and transit. A path between the stairs and elevators was colored due to its impracticality. Profiles. User profiles were implemented and differentiated through their routes, interests, speed, angle of vision, vision distance, and weight. Interests would dictate where they would go during their travel, where they would stop during their travel. Speed dictated their movement force. Angle of vision affected their cone of sight, and vision distance would affect how far they could see and whether they could spot a point of interest. Weight had an effect on speed. As you can see how the profiles are set up, each agent has their own narrative. For example, the lady on the top right, she's a visitor, and from the entrance, she can go to either pastoral care or transit. Along the way, she may visit a kiosk, grab something to eat, and take a seat to enjoy that meal. These variables that influence these agents' characters contribute in delivering authentic agent behavior. Data on the initial floor plan efficiency was collected through timing routes, which delivered an average of 670 units of time. These units of time are defined as such, as the results were ambiguous in what units they were measured in. Heat mapping was used to collect congestion data. The higher and hotter the tiles become, the more stepped on it is. Pathing and desire lines were produced by the agents traversing their routes and stopping at their interests while being influenced by their profile. This information was utilized to alter relevant walls in the initial floor plan, as well as rearrange the existing points of interest. The way the walls were altered was through a combination of desire lines and agent pathing. Points from the intersection of desire lines were pulled to the closest, and large squares on those points pushed away any walls within its boundary, away from the main pathing flow, lessening those walls' influence on congestion. Points of interest were changed through a grid that had pathing-related tiles colored. Interest points were then pulled to the closest tiles, nudging them a little away from the center of desire lines. After testing, the newer, more optimized floor layout is ready to be compared to the results of the initial floor plan. An average time to reach destination for the original plan took 670 units of time, whereas the new plan provided a faster 620. Heat mapping provided insight into how the older plan had more concentrated routes that encouraged congestion, whereas the new plan displays a more spread out pathing, showing lesser congestion. To evaluate the workflow steps, the final output is an optimized layout that not only dampens congestion, spacing out agent pathing and allowing less impeded travel, but also allows for traversal that is quicker, providing a faster, more reliable area to travel through. However, we only explored one group of user profiles, and I think this could be expanded on in the future. The methods in adapting agent pathing to wall and point changes are very flexible, so you could alter and adapt it to anything you want. This workflow can be applied to other areas of the hospital, where a deeper understanding of the complex routine of staff is required. The proposed workflow that this research is spearheading currently addresses a hospital environment, but has uses well beyond this context to be altered for other building usages, such as office spaces, public areas, and it can even be used to cater to emergency situations like fire escapes. These alterations can be achieved through adapting points of interests and catering to different profile groups to make the applied area ideal for efficiency in time and minimize congestion. Thank you. That's what I said. Yeah. I put, yeah. Oh no, I modified. Yeah.
the angle of infinity.
I think it's more of like what you want to do. Say like someone who knows where they want to go, the angle of vision will be sort of more narrow because they know where they want to go. They'll go straight to it. And, yeah. Hmm. Yeah. Yeah. So if you learn that routine, you could just simulate that. Hmm.
Design and generated in an empty area, and in that empty area, in relation to other areas before, you could train a model, design and optimize the issue of certain objects, rooms or facilities or infrastructure. I think that really huge potential to try to bring all the projects down into an earlier stage, make them the tool that we can fit them around from simulating an area object, designing an area. So I think the presentation is quite good. Has so much potential of, if you see the end of airports, for example. Airport is another kind of where time really matters. You want to reduce distances. You want to make to certain points of interest by people. All right, thank you. It goes running as well. So we would like to start at 12:30. The industry partners, the diary, the senior. Okay, if you start at 12:30, again, if you want to take some lunch, maybe go and market some lunch. If it's weekend, eat and watch at the same time while eating and walking.
I can go.
All right.
Ladies and gentlemen, is it good afternoon? Yes, good afternoon. My project is on the visual representation of regulation, specifically for a automated fire sprinkler system. This paragraph was the given outline by my partner, which was code. Based upon this, I began committing myself to preliminary research, which involved in accessing standard documentation on buildings within Australia for a fire sprinkler system, which is Standards Australia. These documents are as listed above. They range from AS 2118.1 down all the way to AS 4118.2.1. The task would be the application of computational components in an interactive visual, within Grasshopper as a visual representation of these regulations, and for architects or non-expert persons to be able to rapidly prototype said configurations. It is quite apparent that within my process that a lot of difficulty is experienced by industry and by individuals who interpret these regulations. They take a lot of time and effort, and they're quite monotonous. with further research into existing case studies, I found Madeline Johansson and Nazmul Khan's papers published in 2017. These were written in parallel with Khan's objective was to generate permissible envelopes from the ingested regulation. And then Johansson was to develop an open source platform to visualize these permissible envelopes. Moreover, there is precedence in automating legal processes. A good example is a tax platform called TurboTax. It allows the autofill of US tax returns for individuals via asking specific questions and allowing them to import their financial earnings. My three main algorithms that were developed were the sprinkler head layouts, sprinkler pipe layouts, and the construction documentation. I found rationalizing paragraphs from these PDF documentations quite difficult to automate within the time frame given. As such, I have settled on a workflow that allows for the ingest of these PDFs and then structuring the PDF data into an HTML, HTML, CSS, and PNG format. As you can see here, the initial data tree is built by assigning the legislative PDF into the program that then explodes it into the respective points where the text and the images are referenced within the HTML database. Rationalizing the myriad of documents was quite easy with simply assigning a data tree location for each heading, and subsequently, as you can see, once the data is structured, it is able to be queried. Querying the data is simply importing these existing HTML files and asking for the specific location point, which corresponds to the title and vice versa. So you have the choice of either doing a text search or by the data location. Unfortunately, existing time limitations has meant that once implemented into my Grasshopper script, there is some bit of manual processing by the user. They'll have to read the body paragraph of the HTML code at this current time. The fundamentals of the sprinkler head layout requires the ingest of maximum and minimum bounds, which then is fed into a script that allows for the user to have the only difficult task of picking the distance between each sprinkler head within the allowable bounds. So the script will notify the user if they've inputted an invalid option, allowing for more of a stupid proofing, more or less, the experience. As you can see, with varying X and Y distances, the sprinkler heads will generate. Furthermore, the piping script facilitates the division of major supply piping to the next section, and then to the subsequent sprinkler. This script also has the capacity to correct piping to avoid certain obstructions like a column. If you identify these values or place certain set fitnesses to the script, it will attempt to meet your requirements as best as possible. And furthermore, the sprinkler layout documentation structure is the CLT frame. The CLT frame involves the visual showcase of where the cutouts would be. As such, these geometries within Grasshopper can then be exported into a format that can be incorporated into a BIM, or if rapid prototyping, you can even just laser cut, export for a laser cut ready model or a 3D printable model. Ideally, for future, for what can be improved in the future, I would like to develop the natural processing language to ingest the paragraphs upon paragraphs of regulation into values that can be rapidly inserted into the already built components that facilitate certain aspects of the requirements to speed up and limit the error rate of individuals having to consider a sprinkler layout within their geometry structure. Yeah. Yeah. Honestly, there's the visuals aspect of my outcomes aren't really pretty. A lot of the work was focused on developing robust scripts that can handle structured data and allowing for irregular geometries, allowing for layouts, allowing for then additional components that will be developed later on. I found it quite difficult without a base, realized full geometry-based model. I think if I, at a later date, had that and I had more precise requirements, like I have to consider the layouts for the stairwell or all those other parts of a building, I think it would make it a bit more complete in a sense of usability.
Day-to-day things that take a lot and beyond. Eventually, makes people leave. And now, a very close friend of mine left a very, very big office. Some people have been engaged with, because his main job was sort of following up regulations. If train station design meets the regulations from the other.
Yeah.
So he spends hours and hours and days measuring something. Why not? It's a stairs right stuff. It's a similar.
I asked three. What are the possibilities? Evidence that actually, like, we're never going to use your things. By if you make it like I don't know. If I am looking at in because the data is, I can't even just yeah, exactly.
It's just about you could say that just the regulation, and the steel regulation is 2 meter 55, you got 2 meter 55 compound.
Yeah, but also because there's no point of like if you don't know like it's always like because they have to work with teams and these extreme.
All right, thank you for that. Well done. Very favorable. All right, see you again.
They want to do.
Oh, it's quite beautiful. All my analogies are quite beautiful. Like every image diagram, every paragraph of text, every corresponding linking reference is all